Hi everybody. Today I'm going to kick off our Unit 5 work by a little discussion on the center of mass and how objects rotate. It should be a real quick video, I hope, so we're going to just jump right into it. First and foremost, I know as you look at this page, your eyes are immediately drawn to this cool picture I found. Um, we know now, since we've discussed Newton's laws of motion, that when you apply a force to an object, you can get its motion to change. Um, Up until now, though, when we've drawn out a free body diagram, like for example, this one right here, there's a box, and we have a person who wants to move the box, and so that person applies a force in that direction right there. And we could also draw the other forces involved, right? The normal force and the gravitational force. And let's assume that it's frictionless and air resistance is really low. So we end up with that free body diagram. But my question for you is, what is this point that I've drawn them all from? Did I just draw them from some central point? Or is there a real physical meaning for that little point there? And it turns out there is. It's something special called the center of mass. It's the place that we can assume that all of the translational forces act on the object. Center of mass. Sometimes it's called the center of gravity for this very reason, because it's the central location which we can assume the gravitational force acts on. So you can imagine, if you're looking at this box here, that this little part down here has mass, and this little part down here has mass, and this part up here has mass, and that part up there has mass, and each one of them is getting attracted to the Earth, right, to the center of the Earth. But on average, if we averaged out all those forces, we should be able to find that the average force acting on the object, because it's all connected together, is actually at this place that we call the center of mass, or sometimes the center of gravity as well. So center of gravity actually has a kind of a special meaning, which we'll talk about later on when we talk about how things orbit. But for now, I'm just going to use center of mass. This center of mass thing is totally independent from the rotation of the object. So if you imagine somebody sliding a wrench across a table, particularly a table that has a very low friction, what you'll see is it rotates around as it's sliding. You can see how it's rotating through this image here, and it makes a cool wave pattern as you can see it. But anyway, what you notice is if you looked at the center of mass of the wrench, which happens to be about right there, you'll notice that that center of mass does something interesting. And that center of mass, that was my cat, sorry, center of mass moves its way across the table in more or less a straight line. Why would it have to do that? Well, remember Newton's first law of motion, that objects will tend to move in a straight line at the same speed unless acted upon by an outside force. In this case, if we assume there's no friction, once you get it started, there's no forces acting on the object that are not balanced out. And so what we end up having here is motion in a straight line at the same speed, or with a constant velocity, because there's no net force acting on it. And so you can see Newton's first law playing out here in the locations of the center of mass of the wrench as it moves across the table. I think that's pretty cool. So that's Newton's first law. But in the process, you can see that the wrench is rotating, right? It's moving its way around in a circle, as you can see, like so. And so it's kind of curling its way back here, which is kind of weird. So it ends up curling its way back, and so on, and then back again. So it has kind of complicated motion, which is kind of interesting. But the whole point here is that you understand that the center of mass obeys Newton's laws of motion pretty much word for word, as we would hope. And so in our heads as physicists, we tend to assume that all of the mass is located right there at the center. So rather than deal with the motion of a wrench, which is complicated and weirdly shaped, and might do things like rotate, which are harder to describe, I can go ahead and assume that all the mass is at the center of mass, as if it was all compressed down into this one little point. And that one little point moved across the table just like Newton said it would, which I think is pretty cool. Now, if it's important to you to describe the rotation, that's cool too, and that's actually what we're going to be talking about here in this first week of this Unit 5. Objects do rotate, and they can change their rotation. And so this wrench probably wasn't rotating at first, but then somebody slid it across the table in such a way that it was rotating. I think that's pretty cool, and you can see the interesting motion that it has. But one of the things that's important to know is that there's a special way that you can apply a force not to the center of mass, and that will cause a change in its rotation. Again, this wrench changed its rotation because a force was not applied to the center of mass. And so that's going to set us up for this idea called a torque, which is what we're going to talk about later in the week. And actually, it's what most of Quest is about this week, so you want to make sure that you've seen that before you do any of the Quest work. Now, one thing that's important to know is that we oftentimes have to talk about how fast something is rotating. And we also have to talk about the word rotation, because I want to make sure that you understand what I'm talking about when I say it. This word rotation is something that I'm sure you're familiar with. You've heard it before, you probably used it before. And in physics, just like many words, rotation has a very special meaning. Rotation is when an object moves around an internal axis. So the outside, the object itself is spinning around an internal axis. So I want you to imagine I've got a merry-go-round right here. And so here's the center of the merry-go-round. So that's our internal axis. You can see that the center is inside of the merry-go-round, right? It's not off somewhere out over here that the merry-go-round is rotating around. It's this central pole that goes down the center. And then let's imagine that you pick a horse that's on the edge right here where this blue X is. Now that means that when the merry-go-round starts up, you're going to start to rotate around along the edge of the circle until finally, let's say, you get back to the original starting location. Now, if somebody asks you, how far did you move, you could tell them in feet or in meters if you wanted to, by calculating the circumference of this circle. And you would just have to do that by taking this radius right here and then multiplying it by 2 and by pi, right? Because the circumference of a circle is 2 times pi times r. And I'm using a capital R here just because I'm an astronomer and we oftentimes use capital R's. So don't freak out by that. It's just a radius. So one thing that's important to remember is that this 2 pi section right there is actually how we define our special units for determining or for reporting out how much of a circle you've moved through. And that special unit is actually right here, which I've warned you about in the past because many graphing calculators are preset for this as the default, and that's radians. This, believe it or not, is the one unit which you can use radians for. And we can talk about how many radians you move through. We can talk about how many radians you move through every second, and we can talk about how many radians per second your angular speed changes every second. So we can talk about all sorts of crazy things that go along with the change in the amount of the circle that you've moved through. But oftentimes that's discussed in radians and not in degrees. So this is the one unit in which this is okay. We're not going to get a huge amount into angular motion, but I want you to be aware of the basics. And so this is one of the basics here. Notice that because of this formula right here, that there are actually 2 pi radians in every full circle. So 2 pi is 6.28 blah, blah, blah radians for every one circle. And so we need to use radians if we're going to talk about the amount of a circle that something moves through. I think 1 or 2 of the questions this week have you used that, but they're pretty basic, so hopefully that helps. Next time, we're going to talk a little bit more about how you get something to rotate and some of the more interesting applications of this and some of the more interesting implications of this. So be ready for that. We've only got a few videos this unit and then a few videos for the next unit. So do the best you can to stay up with it and we should be good to go. Hope you have a good day. Thanks for watching.